Welcome to The Explainer. Today, we're diving into a massive hidden hardware bottleneck that is severely threatening both the scalability and the economic viability of modern AI. Everyone sees the incredible flashy breakthroughs in AI software, but very few people are actually looking at the physical silicon foundation that it all runs on. And right now, that foundation is cracking. We're going to explore some cutting-edge research from Google engineers on exactly how we might solve this impending wall. Okay, let's kick things off with a pretty jarring statement directly from the source material. Large language model inference is a crisis. That is exactly how Xiaoyu and David Patterson, two researchers over at Google, frame the current situation. While training an AI model gets all the glory and the big headlines, it's actually the cost of inference, the everyday usage of the model by millions of people, that ultimately determines if this whole thing is economically viable. Projections are showing that inference chip sales are going to surge 4 to 6 times over the next 5 to 8 years. So the stakes here are absolutely massive. And frankly, the costs of serving these state-of-the-art models are becoming totally unsustainable. So here's exactly how we're going to unpack this crisis today. First, the LLM inference crisis itself. Second, hitting the memory wall. Third, the 4 hardware solutions. And finally, redefining AI system success.
Let's jump right into part 1, the LLM inference crisis, and why AI scaling is actually stalling out.
We really need to shatter this illusion that AI is just smoothly scaling up in the background. The reality is, today's software trends are actively breaking our current hardware. Take mixture of experts, or MO. This involves selectively invoking tens or even hundreds of experts, like DeepSeek v3, which uses 256 of them. This wildly expands the need for hardware communication. Then you've got reasoning models that literally take time to think, generating these long sequences of hidden thoughts before they even give you an answer. Throw in massive long context windows, retrieval-augmented generation that's pulling in custom databases on the fly, and multimodal video generation, and you've got a perfect storm demanding exponentially more memory. Now, the only real exception here is diffusion for image generation, which mainly just demands more compute power rather than memory. But overall, these software trends are rapidly accelerating a massive hardware crisis.
Which brings us to part 2, hitting the memory wall, and the fundamental flaws of our current hardware setups.
To really understand the flaw here, we have to talk about one specific word: autoregressive. When a large language model generates text, it does it sequentially, literally one single token at a time. Think of this autoregressive process like trying to build a bridge, one single plank at a time. But for every single plank you place, you have to walk all the way back to the warehouse to fetch the materials. It's incredibly slow, not because you lack the energy to build, but because you are entirely waiting on memory access rather than your processing power.
There is a really stark contrast between the two main phases of AI inference. First, you have the pre-fill phase. This processes your entire input prompt all at once. It's parallel and it's compute-bound. But then you have the autoregressive decode phase, and that is completely sequential and completely memory-bound. Our current chips are fantastic at that pre-fill phase, but they absolutely choke on the decode phase because they simply cannot access that middle key-value cache fast enough. It's a massive bottleneck.
And the diverging cost trend between these two memory technologies is basically a smoking gun. Current AI processors rely heavily on high bandwidth memory, or HBM. But because it's so difficult to manufacture, HBM capacity costs actually grew 1.35 times higher from 2023 to 2025. Meanwhile, your standard DDR memory costs are actively falling. They've shrunk to nearly half in that exact same time frame. We are financially doomed if we just keep trying to throw more traditional HBM-reliant GPUs at this problem. We are literally pricing ourselves out of scalable AI. Furthermore, inference is entirely tied to real-time user requests. If you ask a chatbot a question, you expect an answer in seconds, right? Not minutes. Depending on the app, we measure this as time to first token, or the time to completion of the entire answer. Because these AI models are so insanely huge now, they have to be split up across multiple different chips, which requires constant, non-stop communication. The latency overhead from these interconnector networks, combined with that slow memory access we just talked about, is becoming completely paralyzing for real-time user experiences.
All right, part 3, the 4 hardware solutions. Let's look at how we actually break through this memory wall. It is definitely time to pivot from doom and gloom to some actual hope. The researchers have proposed 4 incredibly clever hardware workarounds. You can think of these as the keys to unlocking this massive puzzle of capacity, bandwidth, and latency. We're looking at high bandwidth flash, processing near memory, 3D memory logic stacking, and low latency interconnects. Let's break each of these down and see exactly how they work.
Solution number one is high bandwidth flash, or HBF. This basically takes flash memory and stacks it to deliver an absolutely incredible 10x capacity boost with high bandwidth. This means we could potentially host giant mixture of expert models or massive context windows like, say, a billion-page web corpus on much, much smaller systems. But it does have weaknesses. Flash memory wears out if you write to it too much, and the reads are high latency. So HBF is really perfectly suited for things that don't change very often, like frozen model weights, rather than dynamic data that's updating every single second.
Moving on to solution number 2, and this one directly addresses bandwidth. For decades, the industry pushed this idea of processing in memory, or PIM, which meant putting compute logic directly onto the memory die itself. But memory banks are tiny, which means you have to chop your AI model up into thousands of little pieces, which is a total software sharding nightmare. So instead, the researchers are proposing processing near memory, or PNM. By placing the memory and the logic nearby on entirely separate dies, it drastically reduces those sharding restrictions and lets the logic chips run a lot faster and cooler.
Now, the third solution literally builds upward. 3D memory logic stacking totally abandons our traditional flat 2D hardware layouts. Instead, it uses these vertical connections called through-silicon vias to drastically widen the memory interface. This gives us unbelievable bandwidth while saving 2 to 3 times the power simply because the data literally doesn't have to travel as far. It's brilliant. The main catch here? Heat. Cooling a 3D design is significantly harder because there's just less surface area, so engineers will have to run the compute logic at slightly lower clock speeds just to manage those thermals.
Finally, solution 4 focuses entirely on how all these separate chips talk to each other. For massive LLMs running across multiple chips, the network is literally everything. The researchers really emphasize that for frequent, small network messages during that autoregressive decode phase, sheer latency absolutely trumps raw bandwidth. They're suggesting high connectivity physical layouts, like tree or dragonfly topologies. They also suggest doing processing directly inside the network switches themselves, and optimizing the AI chips so they can store arriving data packets directly into really fast on-chip SRAM, completely bypassing the slow off-chip DRAM.
Which leads us into our final section, Part 4, Redefining AI System Success, way beyond just raw flops.
Look, as we look toward the future, it's becoming crystal clear that simply inventing new hardware just isn't going to cut it. We have to fundamentally change how we measure success in this space. For years and years, hardware makers have bragged about flops, floating point operations per second. But as we've learned today, having sky-high flops on a giant piece of silicone is completely meaningless if that chip is just sitting there twiddling its thumbs waiting for memory. We've got to stop judging hardware by raw flops. Instead, the researchers argue we must heavily optimize for modern efficiency metrics. Realistic performance normalized against the total cost of ownership, average power consumption, and crucially, the carbon dioxide equivalent emissions of our data centers. Power and carbon have to become first-order optimization targets from day one. But to actually get there, we have a massive cultural hurdle to overcome. Just look at this incredibly jarring statistic. Back when one of the authors started their career in 1976, about 40% of the papers at computer architecture conferences came from industry. By 2025, that share had plummeted to below 4%. This highlights a staggering historical disconnect between academic research and commercial practice. The industry is closely guarding its secrets, and academia simply lacks access to realistic commercial simulators to test their ideas. This gap absolutely has to be bridged if we are going to collaboratively solve the colossal challenges of AI inference.
So here's the ultimate question we have to ask ourselves. The current hardware philosophy of building these giant, high-flop chips is a profound mismatch for the fundamentally autoregressive nature of LLMs. Will the industry step up, reconnect with academic research, and aggressively pursue these 4 solutions, high-bandwidth flash, processing their memory, 3D stacking, and low-latency interconnects, or will the memory wall stop the AI revolution dead in its tracks? We're going to leave you with that final thought to ponder, as the race for sustainable, scalable AI hardware really becomes the most critical engineering challenge of our time. Thanks so much for joining us on this explainer.